Chapter 5 starts off with a section that reminds us of how Chapter 2 started off. Back in Chapter 2, we had something that was called the velocity problem. Here we see actually the opposite of that, but how it connects to velocity. So first we start with areas. And essentially we are looking for areas under a curve. And just that phrase does imply that we're talking about below a curve like a function, but also we are also implying as we start this off that the curve is above the x-axis. So for example, if I have a curve that looks like this, we can call that y equal f of x. And it's above the x-axis because that's the horizontal axis. What we start looking at is we want to find the area under that curve in a certain region from A to B along the x-axis. And so if you just draw a little line from A and B, you're essentially getting this shaded region as the area that you want to find. So the way that we do this is we chop up that region into smaller sections. So how do we do that? Just by using rectangles. And from each of these points here, I can draw a line up to the curve. And then I can use endpoints to find the rectangular shape. So how do I do this? Well, first of all, we have to define a couple of things. We define the width of one of these regions as delta x. So delta x is equal to b minus a, which is the total width of the whole region, divided by how many little regions did I make. We can call that n rectangles. What are the endpoints? Like this one will be x1, x2, etc. A is x0 and b is xn. How do we find the locations of these endpoints? Well, x1 is just start at A and add one value of delta x. x2 is start at A and add two values of delta x. So in general, xi is just start at A and then add I values of delta x. So now what if we used right endpoints of our regions? That would mean, like in this first rectangle here that is starting to be implied, I would use the right endpoint of the interval to get the height of the rectangle, and then to finish the rectangle I will just draw a little bit more. So if we were using right endpoints, then we could add all of those rectangles up. The sum of them would be capital R for right endpoints, sub n, because I have n rectangles that I'm adding up, and that would be, they all have the same width, delta x, times f of x1, because you can see the first interval is using x1, f of x2. When you're plugging those numbers into the function, you're getting the height of the rectangle all the way up to the last right endpoint, which is xn. So then the area is just the limit as n approaches infinity of that sum. While in my picture I only have a few rectangles, the idea is that we would like an infinite number of very small rectangles, and then we find each of their areas and add them all up. If we use left endpoints, we're just using a different starting point and ending point. We still have delta x as the width, but the first left endpoint would be A. And the way that the left endpoints would work is if I used A to get my first height, then I would get a rectangle that is below my function. So what you start to see in the wording of this lesson or in this section is upper and lower estimates for the areas. And it depends on if you're using right or left endpoints, but it also depends on what's happening with the curve as well. Like if I used a left endpoint here, I would get a rectangle that's above the curve. So really the idea is that if you use the right endpoints for the whole function and then use the left endpoints for the whole function, you'd get an upper and lower bound for this area. So then for the left endpoints, the values that I plug into my function start at x0 and then goes to x1 and then goes all the way up to the one just before the last value, which is written as x sub n minus 1. That would be right here, x n minus 1. And again, if we take the limit as n approaches infinity of the sum of these left endpoints, then we get our area. So that's how we can find area using left and right endpoints. How does this relate to distance? If an object has velocity or speed, rate of speed, v, which is some function of time, t, over a time interval, let's say a to b, and if velocity is positive, so always moving away, say from the object or from a starting point, so just like a function that's above the x-axis, then the distance that's traveled in that time interval we could say is d, and that's just the limit as n approaches infinity of the sum from I equal 1 to n of f of t sub I delta t. Why is this true? For each small time interval, that's what is implied by delta t, that's the width of that time interval. There is velocity. Those velocities could be changing, but that's okay. For the small time interval, the distance would just be what is the velocity during that small time interval, and you're going to multiply that by the change in time. How do we know that? You might recall from algebra, distance equals rate times time. It's the exact same concept. So velocity is just the velocity function at a particular time or time, which would be an endpoint of a time interval, and then change in time is just delta t. So let's take a look at a couple of examples. First, to practice what we were doing with the endpoints, let's look at number 18. And here we're given a function, f of x equal 1 plus x squared. And we want to find the area underneath that curve in the interval -1 to 1. And so they do give us a couple of directions that say evaluate the upper and lower sums. We're going to do that by just using right and left endpoints. And they also say do this with n equal 3 and n equal 4, but I'm just going to use n equal 4. And this is on page 375. So first I'm going to draw just a little sketch. This is a parabola. I could just plug in the numbers -1, 0, and 1 for x. So example, at x equal -1, the value of the function is going to be 1 plus 1, which is 2. Because -1 squared is 1, and 1 plus 1 is 2. At x equals 0, I get 1 plus 0, which is 1. And at x equal 1, I get 1 plus 1 squared, which is 2 again. So as we expect, we get a part of a parabola that's opening up. So now let's figure out what's the width of the intervals we're going to use. In this case, b is 1, a is -1, and n is 4. You should always expect that the width is positive, so just be careful with your work. 1 minus -1 is the same thing as 1 plus 1. And so we get 2 over 4, or 1/2. And then what are my endpoints? Well, remember x0 is just a, which is -1. x1 would be a plus 1 times delta x, which is just -1 plus 1/2, which is at -1/2. Finding the other endpoints, then just remember that you're adding the width as you move along. So we expect that the next endpoint would be at 0, and then the next one would be 0 plus 1/2, which is 1/2, and then the last one would be 1. And we could write our symbols for these below. x0 is -1, x1 is -1/2, x2 is 0, x3 is 1/2, and x4 is 1. Notice this says the same thing that we said before, xn is equal to b. So, what we're looking for is, we're not going to be taking a limit, we're looking at our estimates, which means what's the sum of the rectangles using right endpoints. In this case, I'd be thinking of r sub 4, and it would be delta x times f of x1 plus f of x2 plus f of x3 plus f of x4. We already have that delta x is 1/2, and we have that x1 is -1/2, so f of -1/2. x2 is 0, f of 0. x3 is 1/2, and x4 is 1. So in this case, using right endpoints, what we're doing is using these to find our heights, and then that creates our rectangles. So how do we find our function values? Well, I've got a function right here. I just plug my numbers in. What do I get when I plug in -1/2? Well, -1/2 squared is 1/4. 1/4 plus 1 is 5/4. We already know what we get for 0. That's just going to be 1. For positive 1/2, we get the same thing that we got for -1/2. And then for 1, we get 1 plus 1 again, which is 2. Adding 2. So what we end up with is 1 plus 2 is 3, 5/4 plus 5/4 is 5/2. Three is the same thing as 6/2. I get 11 over 2 times 1/2, which is 11 over 4. So that would be the area of those 4 rectangles that I've drawn there, and it estimates the area under the curve. If we use left endpoints, Remember, it just means that we start with x0 and we go all the way up to the endpoint just before the end. So we stop at x3 because n minus 1 is 4 minus 1 or 3 in this case. Delta x is still 1/2. F of x0 is f of -1. And then notice we actually repeat the same numbers that we were doing before for a few of these. The value of the function at -1, we already found that, it's 2. We already found f of -1/2, 5/4. We already found f of 0, 1. And we already found f of 1/2, another 5/4. Notice, in this particular case, because of the symmetry of this parabola, we get the same numbers that we're adding up. So in fact, in this case, the left and right endpoints yield the same sum, 11/4. So that shows you how to use right and left endpoints. They do make a note of you can find these estimations with any point in the interval. So x sub I star is a notation that they use for the best endpoint to use. Like if it's better to use right endpoints instead of left, x sub I star stands for that. So they make a note where they say you could also find the area by taking the limit as n approaches infinity of the sum, that's what that symbol stands for, sigma stands for sum, from I equal 1 to n of f of x sub I star. So instead of using right or left, just the optimal or best endpoint, delta x. In fact, in the next section, 5.2, we look at midpoints. And then another note about distance. In section 5.4, we're going to get a very nice thing of how we can find the distance given velocity. But once we get through 5.2 and 5.3, we start to see what that easier way is. So let's move on to section 5.2, where we learn what is called the definite integral. And essentially, that definition takes what we just wrote down, this area. Notice that this is an infinite sum of rectangles using our best representative for our endpoint. So they call that thing this notation. So over here on the left, that is called, or the way that you would say it is, the integral from A to B. That's telling you the interval that it's going over of the function f of x. So that's the definite integral. And it's just a symbolic way to represent we are finding area. Over here on the right, in this section, they also give you a name for this sum that is called a Riemann sum with a capital R. It's named after the mathematician that essentially kind of coined that Riemann sum. It's also important to note that just like in the previous section, we're getting areas out of this. So this gives a number. So then a question would be, when is a function integrable? Integrable stands for you can take its integral or find its integral. So when are you allowed to do that? If it is, as in the function, if it is continuous on the interval. So we need continuity. That's why we talked about continuity back in chapter 2, is setting up all of the stuff that we needed continuity for. So I just mentioned that this section gives you another endpoint to use, the midpoint. And symbolically, instead of x sub I star, it's x sub I with a bar over it. And that bar is standing for average. And an average gives you a midpoint. In this case, it's the midpoint between x with the subscript I minus 1 and x with the subscript I. So between these two sections, you get 3 points that you learn about: right, left, and midpoints. Okay, so let's see how this definite integral works in practice. Number 21, page 389. So what we're going to do in this problem is just find the area under a particular curve. And essentially evaluate this integral. The integral from 2 to 5 of the function 4 minus 2x dx. Now the directions of this problem says use Theorem 4. So Theorem 4 in this section, you can find that right in the middle of page 380. And it's essentially the definition that I wrote above, which would say that it's equal to the limit as n approaches infinity of the sum from I equal 1 to n of f of x sub I. So here they're using right endpoints. Delta x, where delta x is the same thing that we had before, b minus a over n. But in this case, we're given b and a. Remember, b is the end and a is the beginning. So in our case, b minus a would be 5 minus 2. Now we don't have a number of rectangles. They didn't say use n equal 4 or 8 or anything like that. So it's just n. So delta x is written as 3 over n. We're also given in Theorem 4 how to find our endpoints, which is the same thing that we had before, a plus I times delta x. This gives us any endpoint. We know what a is, 2. I, and then we also know what delta x is, 3 over n. So this gives us for xi 2 plus 3i over n. Okay, so to evaluate this integral, we need to find the limit. We're going to have to evaluate a limit. That's why we spent so much time learning about limits before, of a sum. And we have to work our way from the inside out. So we have to evaluate this sum first. So now f of x sub I just means I'm going to plug this into my function, because that's f of x. So f of x sub I is just going to be 4 minus 2x sub I, which then I can replace x sub I with 2 plus 3i over n, and then delta x is what comes next, and we said that delta x was 3 over n. Okay, so now let's plug in what we have for x sub I. So 4 minus 2 times, now I'm going to substitute in 2 plus 3i over n. And now we can start simplifying what we have inside of this sum. So first of all, I'm going to distribute my 2. So 4 minus 2 times 2, which is 4, minus 2 times 3i over n, which will be 6i over n. I can see that the 4's are going to add up to 0. So I've got negative 6i over n times 3 over n inside of my sum. That gives me negative 18i over n squared. So now here's something that we can notice. This sum right here only depends on I. It's only the I that is changing. So the negative 18 is not going to change. It's constant. And the n squared is constant. We can factor out the negative 18 and the n squared, just like we did when we were working with things all the way back to derivatives and limits. We can factor that stuff out. So negative 18 over n squared times the sum from I equal 1 to n of just I. So now in this section, you're given some values of some sums. So if you take a look on page 381, the sum from I equal 1 to n of I is equal to n times n plus 1 divided by 2. This is the sum of n integers, 1, 2, 3, 4, etc., all the way up to n. And there's a formula for that. It's n times n plus 1 divided by 2. So we can use that. I have what I had already had before, the negative 18 over n squared, but then I'm going to multiply that by the value of that sum, which is n times n plus 1 divided by 2. And if we simplify this fraction a little bit, I would have negative 18 times n squared plus n divided by 2n squared. And notice what you have here. You've got the same degree in the numerator and the denominator. We've tackled this in this class. You saw this in pre-calculus as well. How do we evaluate this limit? Well, just divide the top and the bottom by the highest power that we see, n squared. So negative 18 divided by negative 18n squared divided by n squared is negative 18. Negative 18n divided by n squared is negative 18 over n, and 2n squared divided by n squared is 2. As n goes to infinity, 18 over n goes to 0, and you end up with negative 18 divided by 2, which is negative 9. So the area that we get is negative 9. Okay, that's interesting. Why is the area negative? Now that we've finished all this, let's just go back to our function. That's a line, 4 minus 2x. And the interval is from 2 to 5. So I'm going to draw the graph of this. So 1, 2, 3, 4, 5. And f of x, that was 4 minus 2x. All right, so where's the function at x equal 2? Well, that would be 4 minus 4, which is 0. And where is the function at x equal 5? That's at 4 minus 2 times 5, so 4 minus 10, that's at negative 6. And this is just a line, so I only need those 2 points. And so I get this line. So what's this area we're looking for? It's the area, now we can sort of reinterpret this since we're talking about a negative area. It's the area between the curve and the x-axis. Well, that just looks like a triangle with base 3. And what's its height? Well, that's 6 units. And what's the area of a triangle? 1/2 base times height, which is 18 over 2. Why is it negative? Because it's below the x-axis. We put a frame of reference on it. In this section, you'll see other formulas for finding sums. You aren't going to be asked to memorize those, but you will need those for the homework. There's also a lot of properties that start to get discussed as well. So I wanted to do a problem that would illustrate a little bit of that. This is number 38 on page 390. And it says interpret, or I should say evaluate, the integral by interpreting in terms of areas. This whole business of taking a limit of an infinite sum, it starts to become really difficult with much harder functions than just linear functions. So for example, in number 38, we're asked to find the integral from negative 5 to 5 of x minus the square root of 25 minus x squared dx. Now, one of the properties that we have says that we can actually split up this integral into 2 separate integrals. So I can handle the first function, x, and find its area, and then subtract the area related to the second function, square root of 25 minus x squared. So how do we want to interpret this? This is the area under f of x equal x, and the other one is the area under f of x equal the square root of 25 minus x squared. So let's just graph these functions like you saw me do at the end of the previous one, and let's see if we can find the area just using knowledge that we might have from finding areas related to shapes. So for f of x equal to x, well, that's just a line with slope 1 and y-intercept 0. So we can get a little bit of that. If you plug in 0, you get out 0. If you plug in 5, you get out 5. You also, if you plug in negative 5, you get negative 5. So in fact, this is the line that we get. Now, if we're finding the area under this curve, it means the area between the curve, in fact, and the x-axis. These two triangles that I've drawn here have the exact same shape. Right? The base is 5 and the height is 5. So their areas are actually equal, but one of them is negative. What happens when you get their total area, because that's what the integral is standing for, the total area over this whole interval, we'd get 0. So in fact, that's equal to 0, the first part of this. So now what about the second part? Well, let's draw a graph for that as well. You might not recognize what shape this would have, but when in doubt, just plot some points. Like when x is equal to 0, you're going to get square root of 25 minus 0, which is the square root of 25, which is 5. So at the very least, you have a y-intercept that's at 0, 5. But then think about plugging in other numbers of x, like 1, 2, 3. How high could you go? The highest you can go is actually 5, because past that, you're going to start subtracting a bigger number from 25, and you get a negative under the square root, and that's not possible. So in fact, we can go out to the left to negative 5, and out to the right to positive 5. And the shape that we end up with is actually a semicircle. Let's try that again. That area is half the area of a circle, because it's a semi, or half of a circle. What's the area of a circle? Pi r squared. What's our radius? 5. So in fact, we end up with 25 pi over 2. So what's the total area? It's the difference of those two that we just found. 0 for the first integral minus 25 pi over 2 for the second one, and we get a negative 25 pi over 2. Okay, so then the end of these three sections, section 5.3, leads us to a pretty big conclusion. Essentially, finding these areas, we can do that by interpreting the function geometrically and try to find those areas. We can try to use these limits of infinite sums. But what becomes much more powerful and useful, and this then becomes the foundation of Calculus 2, is the fundamental theorem of calculus, FTC. And there's two parts to this. So the first part, if f is continuous, and we're saying this on an interval like a to b, then the function defined g of x equal to the integral from a to x of f of t dt is continuous itself and also differentiable on AB, using similar language from when we looked at derivatives. And the derivative of g is just the function, instead of evaluated at t, evaluated at x. That integral that's part of this theorem, this just stands for the area so far. From A to B. Instead of going all the way to B, we're just stopping at some point called X, and we can find the area along the way, the area so far as we're going over that whole interval. So then the second part of the fundamental theorem of calculus, which you should pay attention to those words, fundamental, means it's pretty important. This is a very important theorem for this whole class. The fundamental theorem of calculus part 2 says, again, if f is continuous, again on the interval AB, then the integral of f of x dx, meaning the area under that curve over the interval from a to b, we can actually find it very easily using what we saw in section 4.9, antiderivatives, where capital F is any antiderivative of lowercase f. So let's see how this works with a very simple example. This is going to be number 25. And what page is this on? This is on page 400. Evaluate the integral from negative pi over 6. Oh, sorry, that's positive pi over 6. Positive pi over 6 to pi of the function sine theta d theta. So we want to find the area under the sine curve over this interval from pi over 6 to pi. Okay, so let's just note that in our case here, this is our function lowercase f. So f of theta, we're not using x, we're using theta as our input. Is that continuous? Yes. It's continuous over all real numbers, especially from pi over 6 to pi. And also, since the derivative of cosine theta is negative sine theta, that also means that the derivative with respect to theta of negative cosine theta is equal to positive sine theta. So why did I bother writing that? Well, this then tells me the antiderivative of sine theta. Essentially just you're undoing the derivative. The antiderivative of sine theta is negative cosine theta, because the derivative of negative cosine theta takes you back to sine theta. So if lowercase f is sine theta, that means that in the language of our fundamental theorem of calculus part 2, negative cosine theta is capital F. So how do we evaluate our integral? Well, it has to be capital F evaluated at b minus capital F evaluated at a. Pi is going to be b, and pi over 6 is going to be a. So this means I'm going to have negative cosine of pi minus negative cosine of pi over 6. Cosine of pi is negative 1. Negative of negative 1 is 1. Subtracting a negative gives me a plus. And cosine of pi over 6 is the square root of 3 over 2. And that's it. We're done. So there is some other notation you can use instead of writing down capital F and all of that. If you know what the antiderivative is, you could also, for this example, since we knew that the negative cosine theta is the antiderivative, and then I'm going to evaluate that at pi over 6 and pi. That's a notational way of writing that, but you still have to get to negative cosine of pi. That's the upper limit of integration, minus negative cosine of pi over 6. That's the lower limit of integration. And then let's look at a couple of examples related to the fundamental theorem of calculus part 1. Number 8 on page 399. we're given that g of x is equal to the integral from 1 to x of the natural log of 1 plus t squared dt, and we want to find g prime of x. According to the fundamental theorem of calculus part 1, g prime of x is equal to f of x. So what is f? That's what's called your integrand, the thing that's inside the integral. But this is a function of t. So how do you make it a function of x? Just wherever you see a t, you replace it with x. So g prime of x is just the natural log of 1 plus t squared. Oop. I got to do what I was saying. 1 plus x squared. Now another example that's definitely important to look at related to this same theorem is number 13. This time what we're given is h of x equal to the integral from 1 to e to the x of the natural log of t dt. In this case, since the upper limit is not x, not just x, but a function of x, to find h prime of x, which is the directions, same thing as the previous problem, we need the chain rule. What does that mean? Very simple in this case. I'm still going to have the function that's the integrand, natural log, but I'm going to evaluate it not at x, but at e to the x. And then I have to multiply by the derivative with respect to x of that upper limit. So in this case, natural log of e to the x, that's just going to be x, and then the derivative with respect to x of e to the x is just e to the x. And so that's it. So that's just one subtle difference. If you have an upper limit of your integral that is not just the variable x, but a function of x, you have to evaluate f at that upper limit and then also take the derivative of that upper limit. Another short example to look at, number 56 on page 400, has this question. What is wrong with this? The integral from -1 to 2 of 4 over x cubed dx equal to -2 divided by x squared, evaluated at -1 to 2, which ends up being 3/2. So you're given all of this. And they ask, what is wrong with that? Well, this is the correct antiderivative. Since the derivative with respect to x of -2 over x squared is the derivative with respect to x of -2x to the -2, which gives you 4x to the -3, which is 4 over x cubed. So that's right. We can assume they plugged their numbers in correctly, so 3/2 is correct. What's the problem? Take a look at your interval. What number is between 2 and -1 that could be a problem? 4 over x cubed is not defined at x equals 0. So it's not continuous. So how would we ever be able to evaluate such an integral? To be continued, you'll see that in Calculus 2. All right, so then finally, one last problem to see something that we can do. Number 30 on page 400, we want to evaluate the integral from -1 to 2, again, but different function. 3u minus 2 times u plus 1 du. So you do have to remember things that you have learned. In my whole conversation in section 5.1 through 5.3, at no point have you seen anything called the product rule of integration. It doesn't exist. So don't start thinking that you can use a product of integrals to evaluate this. That's not correct. So what can you do? Simplify the integrand first. How would I do that? Multiply. 3u times u, 3u squared. 3u times 1, 3u. Negative 2 times u, negative 2u. Negative 2 times 1, negative 2. Now, I can combine like terms. And now let's use antiderivatives. The antiderivative of a constant, 2, is going to be 2 times your variable. It's not x. We've got u in this case, so it's negative 2u. The antiderivative of u would be raising u to the second power, but then I have to divide by that new power. And then 3u squared, the 3 can just carry on through. The antiderivative of u squared is u to the third, but I have to divide by that new power. That's essentially what we saw in section 4.9. That's the power rule for antiderivatives. And we're going to evaluate that at -1 and 2. So I can clean this up a little bit. This turns into u to the third power plus u squared over 2 minus 2u. All of that stuff is going to get our limits. Remember that your upper limit 2 goes first, and then the lower limit goes second, which means I need to plug in 2 for every instance of u. So I'd have 2 to the third power plus 2 squared divided by 2 minus 2 times 2. And then I have to subtract when I plug in my lower limit, which would be -1 to the third power plus -1 squared divided by 2 minus 2 times -1. Don't forget parentheses, especially with negatives. And then we just clean this all up. 2 to the third power is 8. 2 squared divided by 2 is 2. 2 times 2 is 4. -1 to the third power is -1. -1 squared divided by 2 is +1/2. And then -2 times -1 is 2. So I end up with 10 minus 4, which is 6, minus, parentheses, -1 plus 2 is 1. 1 plus 1/2 is 3/2. So this gives me 12/2, because that's what 6 is, minus 3/2, and that gives me 9/2. Remember, we said that our integral will give us a number. And so in this case, we get the number 9/2 for the area that's under the curve, in our case, 3u squared plus u minus 2.